Webb's groundbreaking discovery of a gravitationally lensed supernova offers solution to the Hubble tension. The James Webb Space Telescope, JWST, the most advanced space observatory ever launched, has once again delivered a groundbreaking discovery, this time with potential implications for solving one of the greatest mysteries in modern cosmology, the Hubble tension. This tension refers to the persistent discrepancy between different measurements of the universe's expansion rate, known as the Hubble constant, h. The discovery of a gravitationally lensed supernova by Webb may provide critical insights into this issue, offering new ways to measure cosmic distances and potentially bridging the gap between conflicting results. Understanding the Hubble tension. The Hubble constant is a fundamental number that describes the rate at which the universe is expanding. For decades, scientists have sought to measure h through two primary methods, local and distant. The local method involves observing nearby objects, such as Cepheid variable stars and Type I supernovae, and calculating their distances using established relationships between their intrinsic brightness and observed brightness. This method gives a value for h of approximately 73 kilometers per second per megaparsec, km/s/mpc. The second method relies on observations of the cosmic microwave background, CMB, the afterglow of the Big Bang, which reflects conditions in the early universe. By using detailed models of cosmology, scientists can infer the Hubble constant based on the structure and distribution of galaxies in the early universe. This method typically yields a lower value for h, around 67 kilometers per second per mpc. The tension arises from the fact that these two measurements, while derived using entirely independent approaches, yield significantly different results. Despite increasingly precise measurements, the discrepancy has persisted for years, leaving astronomers puzzled. The Hubble tension has sparked intense debate, as it challenges our understanding of fundamental cosmological principles and may point to new physics beyond the current standard model of cosmology. The role of gravitational lensing in cosmology. Gravitational lensing occurs when the gravitational field of a massive object, such as a galaxy cluster, bends the light from a more distant object, such as a supernova. This phenomenon, predicted by Einstein's general theory of relativity, can magnify, distort, and even create multiple images of the distant object, depending on the alignment of the lens and the background source. Gravitationally lensed objects, especially supernovae, are of particular interest to cosmologists because they can serve as cosmic rulers that help refine distance measurements across vast scales. The key lies in the time delay between different images of the same event. For example, in the case of a lensed supernova, the light from different images of the explosion reaches Earth at different times due to the varying paths the light takes around the lensing mass. By measuring these time delays and using the mass distribution of the lens, scientists can derive precise distances to the supernova, which in turn can provide an independent measure of the Hubble constant. This method is relatively free of the uncertainties that affect traditional distance ladders, making it a powerful tool for resolving the Hubble tension. Webb's discovery of a gravitationally lensed supernova. In its mission to explore the deepest reaches of the universe, the James Webb Space Telescope has made a remarkable discovery, a gravitationally lensed Type I supernova in a distant galaxy. Type I supernovae are often referred to as standard candles because of their predictable brightness, which makes them ideal for measuring cosmic distances. The discovery of a lensed version of this phenomenon offers an exciting opportunity to further refine these measurements. Webb's advanced infrared capabilities allowed it to peer through clouds of gas and dust that typically obscure distant objects, capturing the lensed supernova with unprecedented detail. The telescope's sensitivity to longer wavelengths also enabled it to observe the supernova at a much greater distance than was previously possible with the Hubble Space Telescope. This discovery represents a major leap forward, as it not only allows for precise measurements of the supernova's brightness and distance, but also provides a new method for tackling the Hubble tension. The gravitational lensing of the supernova created multiple images, with light from each image arriving at different times. By carefully studying these time delays, astronomers can use the lensing geometry to calculate the expansion rate of the universe. Crucially, this method is independent of the traditional distance ladders, offering a fresh approach to measuring the Hubble constant and potentially resolving the tension between local and distant measurements. How this discovery could resolve the Hubble tension. The key to understanding how Webb's discovery might resolve the Hubble tension lies in the ability to measure distances with unprecedented accuracy. One of the primary sources of uncertainty in traditional methods is the calibration of the distance ladder, especially the local measurement of h, which relies on calibrating Cepheid variables and type I supernovae. Gravitational lensing, on the other hand, offers a way to directly measure cosmic distances without relying on such calibrations. By studying the time delays between different images of the lensed supernova, astronomers can determine the distance to the supernova independently of local distance ladder methods. This provides a powerful new tool for measuring the Hubble constant. If the value of h derived from the lensed supernova matches the value obtained from CMB measurements, it could indicate that the local measurements have systematic errors, potentially resolving the tension. On the other hand, if the value of h derived from the lensed supernova matches the local measurements, it would suggest that the CMB-based value is incorrect, pointing to new physics at work in the early universe. In either case, the discovery of a lensed supernova offers a critical new piece of the puzzle. Implications for cosmology and future research. Webb's discovery of a gravitationally lensed supernova has far-reaching implications for our understanding of the universe. If this discovery helps resolve the Hubble tension, it could confirm that our current models of the universe are sound, and that the discrepancy is due to previously unaccounted-for systematic errors in one or both methods of measuring h. However, if the tension persists even after incorporating the new data from lensed supernovae, it may indicate that there is something fundamentally wrong with our current understanding of cosmology. This could suggest the existence of new physics, perhaps modifications to general relativity, the presence of exotic forms of dark energy, or interactions between dark matter and ordinary matter that have yet to be discovered. Webb's ability to observe distant, gravitationally lensed objects with such precision also opens up new avenues for research. Future observations of additional lensed supernovae could further refine our measurements of the Hubble constant and help distinguish between competing theories. Moreover, Webb's findings will complement other observatories, such as the Vera C. Rubin Observatory, which is set to begin operations in the coming years and will conduct large-scale surveys of the sky, potentially discovering hundreds of gravitationally lensed supernovae. Conclusion: a path forward for solving the Hubble tension. The James Webb Space Telescope's discovery of a gravitationally lensed supernova is a game-changing development in the ongoing effort to resolve the Hubble tension. By providing a new, independent method of measuring cosmic distances, this discovery offers a fresh perspective on one of the most pressing issues in modern cosmology. Whether the Hubble tension is ultimately resolved through this new data or whether it points to new physics beyond the standard model, Webb's findings will have a profound impact on our understanding of the universe. As astronomers continue to analyze the data from this and future observations, the JWST stands poised to unlock new insights into the nature of space, time, and the fundamental forces that shape the cosmos. In the coming years, the combination of Webb's advanced capabilities, the power of gravitational lensing, and the discoveries of future observatories will provide a more detailed and accurate picture of the universe's expansion history. With each new discovery, we move one step closer to solving the mysteries of the cosmos, and perhaps, finally, to resolving the Hubble tension once and for all.